about RLHF, there's a lot of interest in how ChatGPT was built. Before I get started, a quick show of hands. How many of you use an LLM like ChatGPT on a daily basis? Show of hands. Oh, wow, everyone. How many of you were training neural networks before ChatGPT? A show of hands. Oh, okay, good chunk of you. Okay. So then what I'm going to do is I'll blitz through the first part of the talk, right? So these are our robots. Here's an old version of our robot Mitra with Prime Minister Modi and one with Dada there, the newer one. They've been on stage more than I have. But we also do other kinds of R&D. This is with the University of Maryland. This is for working with brain-computer interfaces. So if you think of, let's say, bring me food or bring me water, and the robot has an arm and it'll go fetch it. And then we've had some real-world deployments in geriatrics, in elderly care for people with dementia and things like that. But I'm here to really talk about AI. This is India's largest AI conference. We're here to celebrate AI. Robotics happens to be one of the biggest use cases of AI. So let's start with part one, the story of AI, and how did we actually get to the ChatGPT moment. So the story starts almost 80 years ago, in the 1940s, with Warren McCulloch and his protege, Walter Pitts, who figured out, he was a neuroscientist. He was looking at the brain. He was like, how are these neurons firing and what are they doing? And they conceptualized this McCulloch-Pitts model, which is basically a lot of signals coming into the brain cell, accumulating, some computation going on, and then a signal goes out to the axon to other neurons. So can we simplify this? And then they realized that the theoretical aspects of whatever you had with logistic regression back then, there were no computers at that time. They were all done on paper. So it's just a bunch of signals coming in, weighted, getting summed up, and then choosing to activate. And they had the realization that logistic regression is nothing but the mathematical representation of one nerve cell, right? The human neuron. So this is the McCulloch-Pitts model, and that's where we started with one neuron. And right today we have 175 billion neurons in ChatGPT. So the key idea is that there's a bunch of inputs coming in. They're all getting weighted. There's a weighted sum, as you all know. And then you apply a sigmoid function, some kind of activation function, and then it chooses to fire accordingly. So this leads to a flurry of activity, and then there's the first AI summer, the Dartmouth conference in 1956. John McCarthy is the guy who comes up with the name artificial intelligence. He goes to Stanford to do other things, and Marvin Minsky, AIM gives out Minsky Award, so he's father of AI. And then Claude Shannon, who invented the word bit, and without him, there's no information theory, and so no information science, and no information technology, and we wouldn't be here. A lot of Nobel laureates, Simon and Newell. But Arthur Samuel, one of the guys in the conference, goes on to create machine learning, right? Learning from data. Though he himself is not a great checkers player, he teaches a machine what a good board position is and what a good board position is, and teaches it to classify and play against itself. Eventually, it got better and was almost able to beat him. This is in the 60s. And on the side, people were trying to take McCulloch's Pitts model and try to actually build the neural network. And Frank Rosenblatt comes in the 50s and says, let me wire this up. We don't have digital computers. They're just literally electricity passing through the wires. They hook up all these neurons and get it to work. To some level, the perceptron was the first neural network. And then Minsky and Papert come in and talk about you don't just need one layer, you need multiple layers so that you can learn more advanced representations. So this I call the middle ages of AI, and now we are at the standard representation of the neural network, what we are still familiar with even today. Inputs coming in layer after layer, they get processed, and finally you make a prediction and you keep training it. Now, obviously, this led to a big hype cycle. There was a lot of interest, and then it also led to the neural network net winter, because these models weren't able to keep up. The computers weren't powerful, the data sets were not strong enough. But the field took a sharp turn. And then what happens is the gurus of good old-fashioned AI, they start building all kinds of software which are great for the compute of that time. So you see great search and planning algorithms, stuff like SLAM that we use in our robots even today come up, and then this classic textbook gets written. And there were people who are still continuing to work in common sense knowledge, this kind of stuff which we have in our heads, which we call common sense, that if I say something, there's a lot of stuff I don't tell you, They say, as an Apple, you already know Apple is red. So how do we program that into the machines? So they created the Psych project and things like that. These are really cool if you go study. They had to build knowledge triplets and all of that and build a language on top. It's a database query. Fun stuff, but none of this we use today. And for those of you who are really interested in the symbolic era, highly recommend taking Pat Winston's MIT Open courseware. It's on YouTube. I learned a lot back in the day from things like this. So neural nets go on the side, and people are building this. Jeff Hinton, probably the godfather of AI, along with his associates, they go and build neural nets because computers are getting faster, and you start creating data sets, and then you come up with a training regime. You split up between training and inference, and then all this start working. And then the big deal in 1986, Rumelhart and Hinton write the backpropagation paper. They figure out that, okay, if you go backwards, right, and you can keep adjusting based on the loss function, you keep adjusting the weights layer by layer, you can get it to nicely train. And they show a bunch of interesting results, but they're still outcasts, right? If you went to an AI conference in the 80s and 90s, so they wouldn't even give them a slot to speak. Neural nets were like that. Everybody was like symbolic AI and stuff like that. But all this changed, but slowly they kept working on the sidelines, and then the data sets got better. Jan LeCun makes the MNIST data set and so forth. And there's a lot of algorithmic advances happening. Fukushima comes up with the neocognitron model. He says, why do we have to look at one weight at a time? We'll look at a bunch of weights, because he looks at the rod and cone cells in the eyes and says, we are not looking at single points of light, we are looking at regions. So maybe we should train them together. And this leads to weight sharing, and then led to convolutional neural networks. Eventually, now you can train on 2D structures, right, and extract features as you scan through the images. And Jan LeCun goes and builds this at the AT&T Bell Labs. You start seeing the first CNNs come into production, reading bank checks and doing OCR back in the day. This is like 89, 90 time frame. All of this is slowly happening, and people realize that the knowledge is not in the neurons, it's in between the neurons, in the layers where the weights are. So when that thing takes hold, and then very good cost functions like cross entropy, binary cross entropy, category cross entropy, all of that takes place, and backprop starts working because data starts getting better, and the compute also gets better. So we slowly head into the summer, and then we get to the ImageNet moment. How many of you are familiar with the ImageNet moment of 2012? Wow, okay. So the ChatGPT moment, which most of us are familiar with in late 2022. So 10 years ago, there was another big moment in the AI community called the ImageNet moment, right? So Ilya Sutskever, who's the brain behind OpenAI, people don't thank him enough as much as they do Sam Altman, but he goes on to work with Jeff Hinton and Alex Kichevsky, and they built AlexNet, the first CNN, which absolutely decimates the competition, the annual ImageNet competition, which was created by Fei-Fei Li at Stanford. So they show that CNNs can learn to classify across thousands of classes, across millions of images, and then all the scientists who are like saying neural nets don't work, they come around, right? They say, oh wow, okay, we should take a look at this, and that's the big kickoff. And that's the time when some of us got into AI, and then it got easier to program because Python ecosystem really converged. Rajat built TensorFlow, and Francois built Keras, which is now a front end for all kinds of backends like TensorFlow, JAX, and PyTorch. Sumit comes in and builds PyTorch, and all that good stuff happened. So now a lot of people are trying to work with the compute and then trying to train neural nets. They're tweaking the alpha, the learning rate, and then the Adam paper by Dirk Kingma comes out. Then loss functions start getting better. You're working with hyperparameter tuning, and then all the wonderful stuff happens. And here am I applying deep learning at every problem out there. Now, then the real big benefits, like I said, start working in computer vision. This is because these are all pixels, right? How many of you can see this Lincoln's face here? It's just numbers that you can read off the screen, because images are literally made of pixel brightness going from 0 to 255. 0 is black, 255 is white, and shades of gray in between. And computers can literally read them, and then you send them into the input layer, and what do? You just multiply and keep adding up. And color, no problem, right? Every color can be made with some redness, greenness, blueness. So there are 3 numbers instead of 1, and you take all of this, and then bam, the neural net is training. So this goes on. And then people start training amazing kernels. This is the weight sharing of Fukushima, right? So you can scan through. Here is Grace Hopper's image, a famous computer programmer. And this small kernel, all -1, with the 8 in between, a big number in between surrounded by small numbers. If you keep multiplying it, so you get a nice edge detector here. So now you know how Photoshop brushes work, right? There's a sharpen filter, there's a blur filter. It's just multiplications and additions, right? So this really took off, and the neural nets learn features like this, and then they can keep scanning. All the wonderful stuff happens. Same with the colored stuff. And then there was research where, Zeiler and Fergus come in, and then they look at, okay, what are these neural nets actually learning? Can we deconvolve and see? So you can see this dark, bright, dark pattern here, and there's a dark, bright, dark pattern here. So that turns out to be, these early layers are learning some diagonals. And you see a green patch here. This kernel is learning greenery. Wherever greenery exists in the image, I'll learn it. And wherever, this is a gradient detector, and this turns out to detects gradients everywhere. And what does it do? It passes on its knowledge to the next layer. The second layer, you can see there is a horizontal edge and a vertical edge here. And what that means is, it's learned to put together a horizontal and a vertical edge together, and it's learning. And what do you learn from that? Corners. And corners exist in what? In every screen and paper and anywhere, door, windows, wherever you have a corner, you learn all of that. And that goes on, and you get higher level patterns in layer 3, 4, and 5. And in the 5th level, it's already learning, humans and cats and birds. You couldn't feature engineer this, right? Literally, gradient descent does all the hard work behind the scenes. So all this came out, and they started really working. And you don't really have to just use this for images taken from cameras, because images are not just what the eye sees and the camera captures. Anything can be an image. So people realize that if I take an audio file, this could be some baby crying or some guitar, you just turn it into a spectrogram, right? And then you throw this into a CNN, and it will learn those patterns, right? There's no process, and now you are processing audio. So you take a bunch of audio files, the same CNN is able to distinguish what's going on. So I was lucky enough to work with an engineer and a doctor he was, and we founded RCE.ai. I used to live in Atlanta at that time. And then we built a model that would take ECG waves. Your Apple Watch will give you ECG wave, 2 lead ECGs, right? But if you go get wired up, so they will see ECG waves, if you look at the heart from every single angle, from the front, from the back. So you could chuck that into a CNN, take a slice of it, and then if you predict, and if there's an elevation in the ST elevated myocardial infarction, also known as a heart attack, you can easily detect that with a CNN, and it worked. And then they've gone on to do great things. All right, but the big change, the big leap came in transfer learning when people realized I don't have to take a neural network and train it from scratch on every single task. Why do you need to do that? You have a school kid, you send them to kindergarten and middle school and high school and college, and you train them. And later on, you'd say, to train on a new task, I send them to kindergarten again. That doesn't work. So you want to teach new skills. So the people figured out they could freeze the later layers and then retrain stuff. And then what do? You train large foundational models and then fine-tune. So what are the foundational models? Stuff like ResNet, invented by Kai-Ming He, who was, I think, at Facebook or Google. Now he's an MIT professor. Anyway, so all this good stuff happens, and then the machines get very powerful, and the GPUs get really, really good. Now, your CPU is perfectly capable of doing all the math. After all, you're just doing multiplications and additions in the neural net, nothing else. And your CPU runs the OS, and it runs the browser and all kinds of stuff. It's perfectly capable of doing that. But how many cores does your CPU have? Like 12 cores or 8 cores, your i7? But the GPU has 3,000 cores. Right? Very dumb, just multiplications and additions it can do, but in parallel, right? So it's more like a cargo ship rather than the fighter jet that you want. So here's the full stack of the NVIDIA stack, and people play around in this layer. You write one line of Python code, model.fit, model.predict, you're good to go. And these days, we don't even do that. We just talk to the model. So anyway, while all this is going on, the NLP side is brewing up. In the Chomsky era, people are talking about how do I learn the rules of grammar, like nouns and pronouns and verbs, and can we play with this? And good stuff comes out, like stuff like NLTK. But then the real big leap is from Yoshua Bengio in the 2000s, where he comes and writes this famous neural probabilistic paper. This is where he introduces the LM task, the language modeling task, which is predicting the next token, which many of you are familiar with. So this is in 2003, but it doesn't really work until 10 years later when Thomas Mikolov says, okay, let's build embeddings for words. Here is a word, a, the, milk, bread, and for every word he builds up a giant spreadsheet, the vocabulary, and for every word he has a corresponding vector, and in the vector is embedded all possible meanings of it. So he's taken the meanings of stuff and embedded them in those vectors. Right? And this starts working really, really well, and you can do math on this. Vector algebra is possible. You can take the word king, you can subtract the word man from it and add the word woman, and it will say queen or princess. Like literally, you can do arithmetic on words. And once you have this, now you can start feeding those words into the model. And you don't want to just feed one word into the model, so you want to feed a sequence. So at this time, we end up with things like RNNs and LSTMs and GRUs. I won't go into too much detail, but all this stuff happens. The problems with the RNNs is that it starts forgetting stuff very easily. By the time you start feeding the 10th word, it's forgotten about the first word. But the real big jump, again, the step function, like in transfer learning there, comes up with Dimitri Barnau, Yoshua Benjo's student, who he says, let me introduce this concept of attention, right? Because attention is all you need. So he says, if you take two words, like two vectors, right, and just multiply them and add them up, just the dot product, you will get a number. If the number is a high number, then it means that those two are kind of similar. And if they are not, if you don't get a high number, if you get a small number, they are kind of dissimilar. This is the idea behind attention. And when you plug it into the RNNs, it starts working really well. But then Ashish Vaswani comes along and says, he's trying to build a better Google Translator, Google Brain, right? It's just a crazy big system. He wants to turn that into a neural net. And he says, you know what, this attention is working well. The skip connections are good, layer norm. Let me build an architecture which just has only this, no fancy stuff, just attention blocks, skip connections. And it works, and it really, really works. And all the scaling laws and stuff that you see that I'll show you are a result of the transformer model. And then once it starts working well, the people at OpenAI, or like Alec Radford and Ilya Sutskever are paying attention. They're saying, you know what, we should really get going on this. This model seems to, whatever you throw at it, any sequence of discrete tokens you throw at it, it seems to learn, right? Because there were amazing things, the CNNs and the RNNs that they couldn't handle. So the original transformer was built for a translation task. So there's an encoder and a decoder. The encoder runs only once. You feed an English sentence, and you get a state. A vector comes out. And then the decoder is the one which runs autoregressively. It predicts one token after another. How does it know when to start predicting? You just have another token called beginning of sequence. You feed that in, and then bam, 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 it just goes on and on until you choose to stop. Or you say, if you encounter a full stop or an end of sequence token, you stop. So this is how Ashish and Vaswani and team built it. But then these days, we don't have the encoder. We only have decoder models. So why have separate things? So BERT was the first big success story. How many of you have heard of the BERT model? Wow, OK. So the BERT model cites a famous paper called ULM Fit from Jeremy Howard and Sebastian Ruder. So Jeremy is my guru. Everything I know, I learned from him. So they created the idea of transfer learning in NLP. Before that, people wouldn't do pre-training at all. So people would simply say, I will train from scratch, right? But he says, of course, if it works in vision, it should work here. And then they wrote a paper called ULM Fit, which BERT cites, and then they went on to do it. They just read the text both ways, bidirectionally, and then they created an encoder model, which you can fine-tune for further downstream tasks. And then you have all the cousins of BERT after that, and then Hugging Face is full of BERT stuff, which is all good. They all worked, and you should still use them. But then the transformer really changed the thing. It's a very simple model because attention is all you need. Hope you're all paying attention. And then the core idea is like this, right? So you take, this is self-attention. You have a sentence. See how they tokenized it? The word didn't is like didn't, and apostrophe and T. So it's a beautifully tokenized, and you have the same sentence there. And every word is like querying the neighbors, right, including itself, and says, you see a strong orange signal when you compare the word it with the animal, when you multiply, when you do the attention. It means now it is learning that the word it refers to the animal and not the street. The animal is tired. The street is not tired, right? So that's how it figures out ideas layer after layer, and this attention can be implemented in so many ways. But what Ashish Vaswani, Aiden and Nikki and others, they figured out is there's implemented in the form of a scaled dot product attention, because softmax is easy to compute, GPUs do it. So you can do all the matmulls there. So this is how it looks. So all you had to do is give them positional encoding, tell which number comes first, because when you feed it all in parallel, unlike an RNN, it wouldn't know which the order in the thing comes first because we speak words in an order. So you put 1, 2, 3, 4, that's the push line coding, then the self-attention block, the skip connections, and then the fully connected layers. It's a very straightforward neural network, but it just works. Any data, you throw genome sequences at it, Professor Anima Anandkumar at Caltech, so she works with genome sequences. Anything that you throw at it, it just works. And I'll show you in my robotics how we do it. And all the scaling loss that you get is basically something that comes from the transformer, because it just scales. Like now we are thinking of the data wall. Are we going to run out of data? Should we create synthetic data and stuff like that? So this is what it is. The more compute you have, the more data you have, you can keep on training, and this is in the log scale. So Ilya and Alec Radford and others, they figure out that we can pre-train now. So the GPT comes in, and then the Chinchilla paper later tells you that you need approximately 20x the number of training tokens as much as the number of parameters you have. Like they say, GPT 3.5 is over-parameterized. There's too many tokens. Okay, and those of you who are standing here, there's a relay room next door. There's seating. You can continue watching from there, right? In case you want to sit down and, yeah. All right, if you really, for those of the engineers here, you want to do this from scratch, highly recommend learning this from Andre Karpathy. It's a free YouTube video. Spend the 1.5 hours. They will literally teach you how to do GPT-2 from scratch, but he teaches you not with words, but with characters. His data set is the collective works of William Shakespeare. Character GPT-2, which is fully open source. The weights are on their Git repo. So he'll teach you how to do that. So fantastic stuff. But the real underlying theory is like autoregressively predicting the next word. The real metric here is called perplexity. It's not Arvind Srinivasa's company. This is a real metric that you do. What do? You take all the probabilities of the n words that you do, multiply them, and then take the negative 1 by n power of it. So let's say I have a sentence, I love to eat ice cream, and then what is the next word? Next word could be anything. It could say be because, or full stop, or very, whatever, right? It's predicting the next word. It's supposed there's a softmax sitting at the top of the neural net, and it's assigning probabilities to each of the words. If it is good, if it's a very good, well-trained LLM, it will give high probabilities to the likely words and lower probabilities to the more unlikely words. But then, initially, it wouldn't know this. When you do this, right, the model is perplexed. It's confused. It looks like a uniform distribution. It will kind of give same probabilities to all kinds of words. But then what does the loss is high, and then gradient descent will come and say, I'll punish you. Which of you layers are the culprit? Let me adjust the knobs. So that's what it does. Standard stuff, and you train. And then the BERT was an encoder-only model, and then we went into encoder-decoder, and then we get into the decoder-only era. Like GPT-3 was the first big deal, right? 2020 is super awesome that it comes out, and that's when I kind of thought I should put this in my robots, and I reach out to Greg Brockman and say, hey, you want to put it on a robot, and he was very excited. And then there's some old video you can see where Mitra is working with the LLM backend. We benefited a lot out of this. Anyway, so prompts and completions, you go to any talk, they'll be talking about prompt engineering and stuff like that. And then I'll skip through some of this stuff. And hallucinations really are a feature, not a bug, because it's literally what the model does. It's trying to pick the next word and has to predict. And then these days it's getting better with tool usage and structured outputs, and you should all take advantage of that. And then we are getting closer and closer to the ChatGPT moment. We're still not there, right? But then eventually we get to this place where Andre says that the hottest programming language is English, which is probably true. All right, so how did they actually build ChatGPT? This is the real talk, right? So how did they actually do it? You need these three things, these three stages: the pre-training, the supervised fine-tuning, and then the RLHF stage. So pre-training is something that they already, this slide I'm stealing from Andre's build conference talk, which you should watch. It's an insane, amazing talk. So the pre-training phase is basically take raw internet, trillions of words, low quality but large quantity, and you do the LM task, Yoshua Bengio's thing, predict the next token as usual. And what you get is the base model. The base model is good. It works, and it takes thousands of GPUs, months of training, and you get something that it really knows a lot of stuff, right? How many epochs do you think they would have run for this entire months of training with thousands of GPUs? How many epochs do you think? They're at 1 epoch. Okay, that's how much data it is, right? Anyway, so this is all the stuff. It has seen the common crawl of the internet. C4 is another 1783 GB. It's seen GitHub. It's seen Stack Overflow. It's seen all the books there is archive. Of course, it's able to write the Java program, write a leave letter in the form of a monkey. Damn, like everything that exists on the internet, it works, right? So next token prediction, as usual, this we stuff. And if your vocabulary at that time has 50,257 numbers, so somewhere 47,356th word would be like the highest probability. That's what the softmax is telling you. You can decode it greedily or beam search or whatever and get it, and you train this. So you do this over and over, and finally you get a base model. But you have to do a lot of prompt engineering. We had a very hard time getting this to work with Mitra, because back in the day, we didn't have vector DVs. Like, I wrote a basic NumPy array in memory that was on the robot's onboard computer, and I will remember conversations, right? Because there's no web app like ChatGPT like today. But then it will still answer questions, but you have to prompt it accordingly. You have to say, here's the context, here's the question, answer, colon, and then you're pushing it to give out the answer. So what do you do to go from the base model to the SFT model, to the assistant level model, where it actually answers your questions, where it knows that so you will have to do this SFT phase. This is the Instruct GPT paper that comes out, where it learns to understand instructions. Explain the moon landing to a 6-year-old. The original base model will say, explain the theory of gravity to a 6-year-old, explain the theory of relativity. It keeps on saying similar things because it's just completing tokens. But the Instruct GPT one, it goes and literally answers the question, literally how you would explain moon landing. And the way they did is they paid a lot of money to contractors. They wrote prompt response pairs, lots and lots of them, with extreme high quality labeling instructions. This OpenAI will not open source, obviously. And then you do this, but 1 to 100 GPUs for a few days of training, and then now it's answering questions, whatever you say it does. But still, it's still Instruct GPT. This is not ChatGPT, right? This is the time when the people in the community are excited and the engineers are going, wow, this works, right? I can deploy this. And you can deploy, but then what happens one day, there's a guy who comes and says, we can make this much better, right? So we got to make this much better. So we got to send it through this alignment phase. Because are these models helpful, honest, and harmless? So you got to do RLHF. Without that, you don't get that extra oomph, right? So if I ask a question, hey, how are you to the model could say, I don't care, get lost. It's an answer, it's answering the question, but is it really helpful and harmless? How do you actually get it to do it? So then you will have to do RLHF. And it's shown to work that humans will prefer even a tiny model's preferences, the answers, to a much larger model without the RLHF. It really seemed to work. So how do you do this? So in order to do this, there are two parts. Okay? So first you collect a reward data set. So reward data set is like you say, you send prompts into a computer, into the LLM, and say, give me responses. And then if you take it to a person and say, rate this on a scale of 1 to 10, people will struggle because people don't know how to rate things. The analogy I like to give is, like, let's say you're opening a restaurant, and then you're cooking dishes, and people are kind of rating them well. But how do you improve the dishes? How do you make sure that these things are preferable to what your patrons want to have? So you ask your chef to cook many, many dishes of the same kind, and you take copies of them to a person and say, between these two, which one do you prefer? So that's a hack, right? So people find it far easier to rank things rather than rate things. So then they figured it out, and then they said, okay, you collect all these things and say gold medal, silver medal, bronze medal, and now you can take pairs of this. These are called preference data sets. With this, you can train a reward model. It's just a binary classifier. So it's just a LLM with a single neuron on top, and it can give classification. This becomes a proxy human, and that teaches you that you kind of get pairs. So the model will say, if a LLM gives you two outputs, which of those will a human will prefer and which one they will disprefer. That's what it tells you. And then comes the reinforcement learning part, which is part 2. All right. So if supervised learning is like perception, what you perceive, then I think of reinforcement learning like judgment. How do you take actions on top? You perceive and then you take action. It's in a loop. So you see Rohit Sharma hitting this ball for a 6. So he's perceiving the ball. He knows the maximum likelihood of the position of the ball, and then he chooses to hit it somewhere. He could have chosen another action because there's a model in his brain which is telling him I have to take this action for the maximum reward, right? Or if it's and it also depends on the environment. If it is a test match, maybe he will leave the ball or something, but you don't know Hitman, you don't know what he will do. But anyway, so this idea became popular with robotics, my stuff, and then with games and Atari games, where these people have an agent, and you don't have a data set, you hook it up to a game engine and you say, the agent is going to give you rewards, right? This is like trying to get a pet dog and trying to teach it. You say sit and it won't obey you, and then you don't feed it or give it a penalty. And if it obeys you, you give it a treat, right? So through reinforcing the good behaviors and avoiding the bad behaviors, these models learn. So this idea of reinforcement learning is important. So how does it really get to ChatGPT? I'll tell you. I'll quickly play a video of the robot. So here you see me gesturing to one of my robots, and then you see it comes towards me, it sees me, and it's always tracking. So there's a bunch of algorithms running behind the scenes, right? And then it is trying to map and find me, always keep me in the scene, and then it is watching for my gestures, it's looking at my hands, and then finally it makes its way towards me. And if I kind of like swivel around, it tries to get closer, it wants to look at my face, and then if I change positions, it can goes backwards and adjust itself so that it's always there. So kind of stuff we do. And if I say, put up my hand and say stop, and then it will stop tracking me and stuff like that. So all of this is great. We benefit from this training regime where the environment is giving out the next state, and the agent learns, positive and negative rewards, and then it takes action in the world. So this constant perception and action loop going on, this is RL. Another example of, if you are in Bangalore, you hit traffic, so Google Maps tells you, if you take this other route, maybe you will save 2 minutes or 5 minutes, okay? And you do it, and then you hit another traffic jam, and you're like, maybe I should not have done it. So sometimes you don't know until you get to the airport whether you actually will save time or not. It's a perceived reward, it's not immediate reward. So basically, you'll have to calculate, you have to estimate how much of an advantage I may or may not get. So this is what the robot learns to do as you do this. So these rewards are quite sparse in RL. In supervised learning, it's straightforward, right? The loss function will say, do better, and gradient descent will keep adjusting. But in RL, the rewards, you'll have to play out the episodes sometimes, right? Only then in the end you will get the reward. But when you get the reward, it's quite insightful. It's because it points you to some of the negative things that you may have done. It tells you how to multiply those gradients with -1 and avoid those wrong things, which SFT will never do. So models also have these other things like explore or exploit. Sometimes they will reward hack. If you've seen RL training, there'll be these Mario-like agents which will go through the game, and it has been told to collect coins, and then it's jumping around and hitting the coin, and it is completely forgotten about the objective of going and meeting the princess. So it will reward hack, and these models will get into that. But then there are unsolved problems. But still, this guy, John Schulman, who is co-founder of OpenAI and chief architect of ChatGPT, he says that I can apply this, right? I can apply this to the SFT model. So I'll do tiny weight adjustments to the model, right? So he comes up with the PPO algorithm, which we'll talk about, and another, Yov Goldberg, another Israeli professor, watches his lecture, and there's a Git repo link there. So he argues why this RLHF is even needed. So supervised learning basically is telling you do better, but it's not helping beyond a certain limit. Whereas RL is like that teacher which says, hey, you need to study that 5th chapter better. It's pointing out those mistakes that you made and is giving you a strong negative signal which gives you that extra boost. And then, but what happens is when you train it with proximal policy optimization, this is the algorithm John Schulman uses to train these models, is what it looks like, crazy math, but just it's just like standard SGD, right? You train it with Adam, and then you have to estimate these advantages. These advantages A is something that you get is like the time you may save, like Google Maps is telling you, the kind of advantages you would say by doing better predictions, you want that to be high. But what they do is they introduce this clipping objective. There's a clip here. So there's another slide. There's a clip here. So what they try to do is they try not to change the weights too much when you're training, right? So what could happen, what could go wrong if you try to change the weights too much from your SFT model? Your SFT model is instruction following. It's answering your questions really well. It's just not helpful and harmless. But if you change it too much, it will forget about answering questions, but it will be very nice to you. It will be like, hey, how are you? So nice. But it will literally forget about the instruction following. You want to have both the instruction following and it to be nicer, so they introduce clipping objective. So they have to learn the RL policy, the model, they have to learn a value function. The RL is like a mess, right? So this is from their older paper called TRPO. But what they're saying is pi is the model, okay? Pi is the model they're trying to train. Pi old is the SFT model. This is the reference model. So a ratio of this should be high. It should get a higher reward. So this part, the first part should be a big number, right? This should be a big number. And what is that thing? What is that they're subtracting? Why are they trying to take away something? That's the KL divergence. They're saying the old models' predictions and the new models' predictions, that it shouldn't diverge away too much, right? KL divergence shouldn't be too high. So the key idea is like try to make very tiny adjustments to the gradients. Don't make it drift away. So it's a check that you put on the training process. With this, if you do gradient descent, they show that it really works. And KL divergence, if you don't know, all the libraries will give you. They just take a ratio of the probabilities for the two predictions, and then they weight it by the actual weight. If it's an important token that you are predicting, and if you screw that up, you need to get a higher punishment, right? So if it's it's weighted. So this is what you want to get. But RL is hard. You can do it. You can go to Hugging Face TRL, which is this Transformers Reinforcement Learning Library. So you can do this. So there's a reward trainer where you train a proxy for a human. It will tell you the preference is good or bad, and you use that and build the PPO config where it is training both the value function as well as the real model. But it's all very tricky. And then, in fact, Andre in his talk says that SFT is achievable, right? He says SFT is achievable. RLHF is in research territory. What does he mean by that? Is he threatening to say like only we at OpenAI can do that? You guys in the open source community, like, all right, challenge accepted, right? So yes, we don't have to do all this. Maybe there's a better way to do this kind of training. Maybe we can do something better than pure SFT, but still gain the advantages of RL without doing RL. And that method is called DPO, right? How many of you have heard of DPO? Anyone here? Okay. So Eric Mitchell, Archit Sharma, and Rafael Rafilov, the guys at Chris Manning's lab in Stanford, a few months after PPO comes out, they realized like there should be a better way, right? We should be able to train this in a much better way and still get that negative signal from RL. So they come up with this amazing paper. So they want this objective. They want, given a data set, and then you have the responses, right, for that. You want a high reward, and you also don't want it to drift away, that KL divergence. This is what is your RLHF objective. But in order to do that, there's a better way to do it. This paper they write called your language model is secretly a reward model. So it turns out that you don't need to do all the RL, but still get the benefits. How? Okay, let's see. So this contraption you will see in our country in many places. So in my mind, what is feeding the juicy sugarcane is basically the data, right? And the juice is the knowledge that comes out, the predictions. And then the machine itself is the neural network architecture, which in this case is a transformer, looks like a transformer. So, but the most important thing on top, which is grabbing, right, the knob, that's the loss function, right? So that's the one you have to squeeze hard. The more you squeeze this, these wheels will crush it more, and then you get that extra juice out. So the loss function is important. So if you just train with cross-entropy loss, as usual, that's just selling do better, and your model is struggling, right? You need very insightful RL-like rewards. So how do you get a loss function? So Archit Sharma and his friends, they go look for a loss function in history, and they find something called the Bradley-Terry model. It's widely used in sports analysis and stuff like that. It's from 1952, okay? So what they say, the model is like a template. So they say in order to create a new loss function, you need some template. So they find this formula. So this formula is like this. You take any reward model. You have to have a reward model, something that tells whether it's a high reward or a low reward. So you need that, but you can take the winner's reward and subtract the loser's reward. There's a big number minus a small number, and then you can pass it through your sigmoid and through a log, which is just like constant multiplications and divisions. So then that big number that you get, that you can maximize. And loss you will minimize, so you multiply by -1 and you minimize. So this can become a good loss function. Okay, now we have a template loss function, so let's find the blue and the red guy. Let's go and build a reward function. So once we build a reward function, we should be able to plug it in these placeholders, right? And then we can do this. So they go again and look for a loss function to be able to get to this objective. And then they There's Sergey Levin's work at Berkeley and other places. This is all basically in 2021, 22, during the pandemic, this is all happening. So what they find is basically a mathematical closed form solution. So what's a closed form solution? So there exists, the mathematicians will simply say there exists, right? You engineers figure it out. So there is an optimal policy. You can get a good model if you have a good reference model, which is your SFT, the base model. It scores very well on the task and also gets a very high reward, but you have to divide by a normalization value. So what it means is they're saying if your model is very good at instruction following and the reward also is very high, then obviously it's both RLHF and SFT are working, but you have to divide by the normalization value. So so this is what it looks like. Okay? So the normalization value, the z of x, is called the partition function, which is a bit of a problem. This is where the mathematicians say you do it, but it's intractable. So why is this a problem? Is this a problem because in softmax also you divide, right? Like you take every prediction and you divide by the sum of them and you get it. For words, it's very easy to take. Your vocab might have 50,000 words, 100,000 words. Your Llama 3 has 128K. That's all easy to do. But we're talking about sequences now. The Z is talking about sequences. Given a prompt, your LLM is giving a completion. What are all the permutations and combinations of sequences you could do? That is like, it's not infinite, but crazy large number. You can't compute that. That's intractable. So that's where we are stuck, right? So we are stuck with this thing. So what do you do? But then Archit Sharma is not the guy who's going to give up. So I tried to do some derivations. They don't put it in the paper, but I'll try to explain. So basic algebraic manipulation. You bring the pi ref, the reference model below, right? Pi by pi. You take z to the other side. Then what you are left is the e to the power of that reward function. The reward function is what we're after. E is the base of natural log, right? So you can take log on both sides, right? And then finally, you can bring the beta term here. So what you are ending up with is a reward function, which is what they were after. So once you have the reward function, they can take this and plug it in. The best part is they have isolated this problematic z guy. It's come out. So you can plug this into the Bradley-Terry loss, the template model. You can take this and plug it in. And then when you do the winner minus the loser, the z term cancels. So this is the key finding, right? The key idea is that just with a sleight of hand, like high school algebra, you can get a new loss function, right? This is a new loss function that you can get. You can squeeze the knob, and then you can continue training with this. Again, these slides are from Eric Mitchell, and he does these beautiful annotations. So now all you have is you have a base model, right? Like the SFT model, and then you're training your RLHF with a new loss function. Just like SFT, you continue training. All you need is pairwise data. No RLHF, none of that nonsense, and you can do it. And guess what happens? In a few days, everybody in the open source community starts using this because it's out in transformers. The results are much better than PPO. And then OpenAI is on a back foot. In a few months from ChatGPT, Llama is out. All the other models are using DPO, and you see the OpenLLM leaderboard. Everybody is hitting that ChatGPT level quality. So that is PPO. There's one more thing. There's a lot of math. Apologies for the non-engineers, but the key idea is you might say, but you might be bluffing. Where is the scale divergence? I saw none of that, right? So that is where this Archit Sharma does this wonderful thing. He says that if you take the gradient, like the new loss function that we have created, if you take the gradient, you will see that you have two numbers here, the winner and the loser, right? So given a prompt, the model gives two things. You run it twice. There's a winner and a loser. You want to reward the winning guy and punish the losing guy. So you want this a high number, and that should be a low number. It's in the right order. But look at the scaling factor that you get for free. So this is the L is in front of the Y. So the loser is in front of the winner. So it's trying to give negative signals. Whenever the model makes a mistake, it's trying to punish that more than the winning guys, right? And if the model tries to reward hack by saying, I don't know, it'll obviously get punished. So there's an implicit scale divergence built into this. That is the most elegant thing, I've seen a paper, so elegant, so beautiful, looking like a wow. But I'm not the only guy praising this, right? It's 4 lines of code to implement. You just take the log ratios, subtract them, and then take the log sigmoid, and then you can continue training. Like, people don't realize how awesome this is. And in fact, the praise comes from people like Andrew Ng. He says, it's only rarely that after reading a research paper, I feel like giving the authors a standing ovation. That's how I felt after I read the DPO paper by Rafalov, Archit Sharma, Eric Mitchell. So they tell you why RL is important, why RLHF is important, why PPO is hard, but then they simplify the whole thing with just a basic algebraic manipulation. They got rid of the Z term, and with a new loss function, you can train. Now, any one of us can use the TRL library. There's a DPO trainer, and we can do. So the open source community should be thanked, right? You should read some of the PRs that come out in, as soon as the papers come out. It's amazing how quickly they adopt and then the community takes to it. And that's how we benefit. So the punchline is basically you can do RL without doing RL because you have this amazing closed form. This closed form solution has been taken care of. All right, so what does Archit Sharma do? He meets John Schulman and says, settle the debate on PPO versus DPO today. This boss move on this thing. So this is where we are. This is how ChatGPT actually happened and what has happened after that. Now, we all can train ChatGPT quality models if we had the GPUs, that is. But then, where do we go from here? What is happening really? What is there to look forward to? So now you've heard of the O1 or the strawberry model. People are saying RL is working now. So why do RL only in that final phase instead of just predicting the final answer? Why can't I use RL to even predict thought trajectories and then try to rank those? If the model has good thoughts, then I would want to rank them higher versus the other thoughts and suppress them. And that is leading to much better reasoning capabilities. It's not there, but it's getting there. And then I talked about all the symbolic stuff in the 80s, and that's coming back. So one paper that I really liked was Alpha Geometry from DeepMind, where they showed that an LLM is working together with a symbolic model, right? So the LLM is the guy who's giving out all kinds of crazy ideas. And the symbolic solver is actually solving for those, and then they get to almost gold level in the math Olympiad, International Olympiad. So all these are amazing stuff to look forward to. There are a few more things. And the thing which really blew my mind is this brain surgery that I call, right, the model merge. People actually go to the weights, and then they figure out, okay, what are these weights doing? And then they try to mess with those individual weights, right? Like you've heard of adapters and LoRa config and stuff like that, but then there are other things people are doing like ties and dare. There's a guy called Pratik Yadav at University of North Carolina in Colin Raffel's lab who does amazing stuff. And then I haven't even spoken about multimodality. This is another big deal what Aditya Ramesh pulled off with Clip and DALI and stuff like that. So with that, we have amazing new things to look forward to, new horizons. Anybody here who's thinking of getting into R&D and working in AI, there's never been a better time. It's been only 80 years since we started with one neuron, and look how far we have gotten. What will 20 more years give us, right? The McCulloch and Pitts, right, the guys who started, they both actually died in 1969 in the same year, just after the moon landing. But before they died, they saw faster computers. Hopefully before Ashish Vaswani dies, we will give them age. But thank you very much. Thanks for patiently listening to my talk.